So let us do one more problem on moment area method. Then we can move to conjugate beam method in the evening. So this is a why I want to uh, show this is because now you can see that in this uh, beam, so this is not continuous. This beam is not continuous because uh, so you are asked to find the displacement at C. Assume A is fixed, B is a pin, and D is a roller, and EI is constant. Use moment area theorem. If you look at this here in this location, there is a uh, pin. So B is a pin. So this beam is not physically continuous. Okay, it's not physically continuous. So for us to apply moment area theorem, you can apply within a segment that is physically continuous. Okay, you can't apply to a segment that is not physically continuous. So let us take this example. So let me copy this. Okay, so the step one, finding the support reaction and plot M over EI diagram. Okay, and what is important here is that the way the the way we are going to find this. Okay, because in moment area theorem, you know that according to the theorem 1, the area covered by M over ER diagram between the 2 points is equal to the difference in the slope between those 2 points. Theorem 2 is the moment of the area between 2 points is equal to the tangential deviation at the point we are studying. So, considering that, now first we had to plot this curve. Okay. So we need to plot this curve. So the first, if you look at the deflection, so this will deform something like this, okay, and then here there is a joint. So if you look at this one, there is no continuity in the deflection, so the other one may deflect something like this. Okay, so the deflection is like that. There is a break here because of the hinge, and we are interested in, we have been asked to find this displacement, that is this delta C. Okay, the question is to find the deflection at C. Now, if you can plot a tangential deviation, now for example, if you can plot a tangent at D, okay, and if you can draw a vertical line, suppose if we have a point in a continuous beam which is a fully fixed, then we can get the deflection relatively easily. But now what we can do is, now we can plot a tangential deviation D, and this we can find, that is delta CD we can find. Okay, so we can do a moment from C to D, and that will be a tangential deviation. Tangential deviation is the distance from the deformed position to the tangent of the corresponding point. So delta CD we can find. Now let us see how we can play around and find this deflection at C. So first part anyway, to work out this moment diagram and then plot M over ER diagram. Since EI is constant, we can plot bending moment diagram and then plot M over ER diagram, which will look similar to bending moment diagram. So now the next step is finding the support reaction. So let me draw a free body diagram. Okay, so this is a pin, and here it breaks. So what I have to treat this as two components. So what I do is, let me erase this part. So if I consider this as a pin, so there will be a horizontal force as well and a 25 kilonewton load. So since in the middle I am straight away substituting the values for the reactions, and this horizontal component becomes HB becomes 0. So now with that, if you consider the AB part, AB. So here we have three. A is a fixed point, so we have three unknowns. So MA, RA and HA, and if you look at point B at B, so this is one point, this is another point. So if this is a reaction, this should be a force on this. So then only when you merge that point, it will cancel it. Okay? So there's the equivalent opposite. So now the load from BD is going to be transferred at B for the cantilever AB. So if you look at this, if this is a cantilever and if there's a beam sitting on that, so this beam, this load is going to be applied as a load on the cantilever. So now that load is 12.5. So if this is 12.5, RA is 12.5, there is no other load. HA is equal to 0 and MA is 12.5 into 3, that is 37.5 kilonewton meter. So these are the reactions. So basically, now you can't do like that in the exam perspective. We will expect you to write some steps. I'm skipping that because I don't want to spend time on doing these things. Okay, so now if you plot the bending moment diagram, so that also we can do in different ways. So the bending moment diagram A, B and C. So between A and B, it will be like a cantilever. So the moment will be maximum. So it will be hogging moment negative 37.5 minus. So it will be a moment diagram like this, and it will be 0 at B because B is a pin. So AB as BC is like a simply supported, so it will be like this. So here the midspan moment again, it's going to be 37.5 kilonewton meter. Okay, so again what I would like to stress is unless otherwise, I mean this is a this curve, this slope is same, okay, although it looks a little broken, it's on the same slope. So this is the bending moment diagram. Now M over EI diagram, so that is going to be the same shape. Minus 37.5 over EI and okay, so A, B, C here and D. Now, if you look at it, finding the deflection at B is very easy. Why? Finding the deflection at B is very easy. Why? Because A is a fixed support, so if you take a tangent of A, it will be the horizontal line, and the tangential deviation from B to from point B to tangent A is going to give you the deflection at B. And if you get the tangential deviation delta C, okay, and if you can get the slope at D, so for example, the slope also depending on between 2 points we can find the slope, right? We can't find the slope at one particular point, only the difference we can find. So what could be the best method? So what can you think about solving this problem? So for sure we can find delta B, that's for sure. Can we use delta B to find delta C? And also if you find this angle theta D, then you can find the delta C, because you can say tan theta D is equal to delta C plus delta CD over 3. And for small angles, we can say tan theta C is equal to theta C, and then we can find it out. So one option is, if you can find the slope at D, we can establish delta C. So how can we find the slope at C? Slope at D. So the slope we can find from moment area method. The difference between the slope is what we can find. And also we can 100% say the maximum deflection will be at C. That is an assumption you have to make. And that can be wrong or that can be right. How to decide whether it is right or wrong? So there is a way to see where the maximum deflection can occur in a that's a way to see where the maximum deflection can occur in a beam. How to find it? How to find it? There is a thing called point of inflection. So point of inflection is where the curve changes from positive to negative. Okay. Can you check what is the definition of point of inflection? You can Google and see. Point of inflection. What is point of no curve of the changes from? Can you elaborate it a bit more? Concave? No, can you read out any other definition? What? Huh? Second derivative? So, what can we do now? Anyway, let us find the delta CD. Okay, can you find delta CD? Tangential deviation at C to tangent D. So that means we are get the moment area curve between C and D and take a moment from C. Okay, can you find it? So the area is defined by this MOIA diagram between C and D. So delta CD is equal to, that's a slash delta CD is equal to, the area is half times 3 times 37.5 over EI. And the distance is going to be, if this is 3 meters, so 1 meter. So that is 37.5 into 3. Divide 112.5 over 2 EI. So that is delta CD. Okay, delta CD. Now, so we got delta CD, and if we get the angle delta theta D, we can get delta C. What can you tell about slope at B? For the segment BD, you can there's a slope at B. There's a slope at B for segment AB, but those two slopes won't be same. Will not be same because there's a pin. Now, if you can extend this curve, okay, you can find what? Delta. You can extend the curve, you can find what? Delta? Delta BD. If you find delta BD, Of course, you can find delta B. Then can you decide the angle theta D? Okay, so let's find out delta BD. So delta BD is the tangential deviation to point from point B to tangent D. Okay, so this is delta BD. So if you look at delta BD, that is the area covered by this moment diagram between B and D and the distance to the centroid. Okay, so that is half times 6 times 37.5 over EI. That is the area. And the distance from B is 3 because the point will be somewhere in the middle. So that is 337.5 over EI delta BD. Okay, 337.5 over EI. And delta B is equal to, so if you take tangential deviation between B and A, from B to tangent A, that's going to give you the tangential deviation delta BA, and that is equal to delta B because tangent A is 0. Okay, so delta BA, so the delta B is equal to delta BA, so that is covered by the area between A and B and the distance to centroid from B. Okay, so the area is half times 3 times minus 37.5 over EI. Okay, EI. And the distance is 2. Okay, the distance is 2. Now, okay, the distance is 2. How about the sign convention? How about the sign convention? So this is 2. So that is 112.5 over minus 112.5 over EI into 2. So that is, so I mean, I just want to know, like we are measuring 2 on both sides, right? So should there be a side? Let us check the text. So for the first theorem, there's no, I mean, just finding the area and then the counterclockwise from tangent A to tangent B. If you measure counterclockwise, it is possible. Okay, so that is for the first theorem. Second theorem, okay, so second theorem, this x bar is what we are looking at. Okay, so the x bar is the distance from the vertical axis through A to the centroid of the area between A and B. So now this is the theorem. Okay, so we are familiar with that one. TAB is the tangential deviation at A to tangent B. So provided the moment of a positive M over E diagram from A to B is computed, it indicates the tangent at point A is above the tangent to the curve extended from B. Okay. So similarly, negative M over EI areas indicate the tangent A is below the tangent extended from B. So in one case, it can be above or it can be below. So if you look at in our case, when you consider AB from the tangent, the B is below the tangent. If you consider CD, it is above the tangent. Okay. Note that in general, TAB is not equal to TBA. Okay, so that is the reverse is not equal. So now when it comes to, so that is all what we can learn from this calculation. Something is negative means it is below the tangent. Something is positive means it is above the tangent. That's all we can say. And the x bar is measured the distance. It doesn't have any sign. Okay, so so the displacement and slope to be determined should be indicated on the curve. Since the moment area theorems apply only between two tangents, attention should be given as to which tangent should be constructed so that the angles and deviation between them will lead to a solution of the problem. In this regards, the tangents at the points of unknown slopes and displacements and at the supports should be considered. So from the unknown, you have to consider a support. Since the beam usually has zero displacement and zero slope at the support. Zero slope at the support is not always correct because only at the fixed support it can be correct. Okay, so this indicates minus 225 over EI indicate that the point B is below the tangent A. The previous positive one indicates that point C is above the tangent B. That's all we can find. So now we have found delta B and we have found delta BD. So delta B is found, delta B is this one, and delta BD is this one. So tan theta D is equal to delta B plus delta BD over 6. Okay? Because we know this delta B, we know this delta BD. So if you sum that, and that will help us to get the tan theta D. Tan theta D is equal to delta B plus delta BD over the distance between B and D is 6 meters. Okay, 6. So now with this, what you can say about at C? So if delta B plus delta BT is X, what you can say about delta C plus delta C? If this is X, what you can say about that? By proportion? By proportion, what we can say? Delta V plus delta BD is X. Means by proportion, delta C plus delta CD is equal to X by 2. Because this is 6 meter, 3 meter. Okay, so proportion, it is half. So delta B plus delta B over D is, it is, so this is tan theta. So then using proportion of two triangles, delta C plus delta C over D is equal to half of delta B plus delta B over D. Okay, it's half of that. So what is the delta B value? Is 225 over EI. Now this sign indicates where it is located, but what we need is a value now. Yeah, we don't care about the sign because that is the problem with these methods because it is not German. So you have to put your effort as well. Okay, you get some values calculating, but you have to have your logical thinking. Now, if you substitute minus 225 here, it's going to be wrong. Okay, so the minus 225 indicate that this B is below the tangent A. Okay, it's below the tangent A. But what I am interested in now, getting a mod value of delta B and delta BD. Okay, mod means sign disaster. And then take the half of that, that should be equal to delta C plus delta CD. I already have delta CD, so I can find delta C. Okay. So I take the value without the sign, so that this is half delta B is 225 over EI plus delta BD is 337.5 over EI. Okay, actually it should be 2 EI, right? 3 into 37.5 is 2 EI. So 225 over 2 EI I'm just wondering how. Yeah, that's correct. 225 over EI plus delta BD is 337 over EI. So the total is 337.5, right? That's 450 over EI over 2 over EI. So then there is another half here. So that is 225 over EI. Okay. So 225 over EI is 112.5 over EI plus 337.5 over EI is 450 over EI into half. That is 225 over EI. So now I have delta CD. So my delta C is 225 over EI minus delta C over D. So that is 225 over EI minus delta C over D is 112.5 over 2 EI. So that is 225 minus 112.5 by 2 is how much? 67.5? No, 57.5? Less than that. So 168.75 EI. Any mistake, any wrong? Delta B 225 over 2 EI. Huh? Yeah, so delta B is the area between B and A, that is this 2 will cancel off here. So it is 112.5 over EI or 225 over 2 EI. Okay. So if I find the values, delta C is 168.2. So the point of inflection will not help you because that is concave down to concave up where the slope changes happen. So only way is you have to. Now you may have studied the trigonometry when you were in the A level. I don't know whether it's still there. Yeah. So we used to love that subject because you can play around with shapes, values, and it's very useful tool. So again here you have to sketch the deflection and then see how you can relate and find it out. So for example, here what we have done is we have sketched, so we know that we can find delta CD, that is the tangential deviation from C to tangent D. Okay. And we know that, okay, we can't find anything with this because we don't know delta C. So then what we did, we extended this curve. So we can, if we can find this value, this is going to be half of that. Okay. So if we can find this value, this is going to be half of that. So when we look at whether we can find this value, okay, yes, we can find the deflection here using this component, and tangential deviation here using this component. So we can find this, and half of that is this value. So with the available calculations and then derivations, we able to find delta C. So let us, when we meet in the afternoon, I'll introduce you the conjugate beam method, and let us redo this same problem with conjugate method and see how easy it is to use conjugate beam method. Okay, because this problem stays fresh in your memory for the next couple of hours. So when we do this using conjugate beam method, we will see the advantage of a conjugate beam method. Okay, so once we finish conjugate beam method, then we move to statically indeterminate structures. Okay, so let us stop here, and I'll see you at 1:30. Let us see whether we can use this hole, because otherwise, check. Yeah, because this one the projector is better. So let's see whether we can use this. We'll use this. Okay. So I'll see you in the evening. Thank you.